All right, everybody ready? All right, so let me, we're looking at the Morris-Lacquer system, and remember the phase plane. Do you guys remember whether I used red or, I don't remember which null line was which. I think this is right. I think that's the right colors. All right, good. So we have this fixed point, and we got this by increasing the current, where it went from something like this to something like that as we increased the current, okay? And we had deduced that this was unstable under certain circumstances, and the solutions were bounded, so there was this big periodic solution. So we had a picture that looks like this. I'm going to sketch out the bifurcation diagram that we have. Okay, and we had let me use a different color for the periodic orbit. We had this big periodic orbit here, okay? I'm only drawing the maximum of the voltage. Remember, this is along this axis. Remember, this is voltage here, and this is current along there. And the Hopf bifurcation, now let me write down the Hopf bifurcation equation. If you recall, it was rho t equals rho times CR, and since the parameter we're using is, let me call this I1, we'll call this I2, and we'll just do the case of I1, so we'll write as I minus I1 plus gamma R, rho squared, and theta t equals Cm I minus I1 plus gamma m rho squared. And remember that the solution to this equation was V of t n of t is V naught n naught. That's the equilibrium right here. Okay? Plus rho, let me write it this way, real part of rho e to the I theta e to the I omega naught t times the eigenvector corresponding to this complex eigenvalue, which I'll write as, what good thing? Here, C. All right, mathematicians like C because it's fun to write, okay? So C is the eigenvector. All right, so there we go. And remember that AC equals I omega naught C. All right, so that's what the solution looks like, roughly, according to normal form theory. So before we go on and fill the rest of this picture, let's solve this equation. Okay, I'm going to leave some of this as an exercise, notably the stability. Okay, but let's solve this equation. What do we get? Remember, rho is the amplitude. And it has to be positive, and it has to be real. So let's solve that. We get rho equals square root of CR I minus I1 over minus gamma R. Okay? Everybody see that? If I solve this is equal to 0, steady state, I get that. You see that? Rho squared equals, bring that over to this side, and then divide by minus gamma R. Okay? So what do you see here? Oh, and what do we assume? Assume CR greater than 0. Why? Because if CR is positive, it means that it becomes unstable as we increase the current, okay? Which we saw here becomes unstable as we increase the current. So what we can see is if gamma R is greater than 0, then I has to be less than I1, right? And if gamma R is less than 0, then I greater than I1, okay? And I'm not going to prove this. This I will leave as an exercise to you to do when you're not playing badminton or ping pong or cricket. I don't know, you guys play cricket? Anyway, as an exercise, it's only this one that gives rise to stable, and this always gives rise to unstable. Well, as it turns out, for the Morris-Lecar equations that we have here, gamma R is in fact positive. So we can fill in the rest of this. What happens is that there's a small I'll just draw it this way. And I pressed too hard on chalk. Okay, so let me say what's good. This you can see, remember this is the voltage, okay? And this is coming down like a square root, okay? And why is it coming down like a square root? Because the amplitude varies as a square root of I minus I1, okay? So everybody see that? And it turns out that it is unstable, all right? Really interesting because it's a small amplitude unstable oscillation, and then there's a big amplitude stable oscillation. So there's a region in here. Let me call this I star, okay? And this is I1. For I between I star and I1, okay? There's a stable equilibrium and a stable limit cycle and an unstable limit cycle, okay? Okay? There is, and we call this bistability. Bistability between an equilibrium and limit cycle. So let me draw the phase plane here without the null line so you can see what it looks like. It's kind of cool, all right? Oh, and let me just fill the rest of this out. It turns out that the same thing happens at this end. It's also unstable at that end, okay? So you have this thing that looks like a mushroom, all right? And the way to interpret this is the maximum of the voltage. This is the equilibrium. Down here is the minimum, but I didn't draw it to make it easier. So basically, if I pick a point of current here, take a slice right there. Let's take that one. Let me call that one IA, and let me draw the phase plane. Okay, so there's a stable equilibrium point. Okay, now we're back to NV. There's a stable equilibrium point. There is an unstable limit cycle, a periodic orbit, and I'll fill in the rest of it looks like this. And there is a, let's see it. Large amplitude, stable periodic solution in this. So what this means, so let me fill in some trajectories here. Trajectories here get stripped off because remember this is a stable spiral. They move off of here. This is unstable, so they whip around here and then they go out to this guy and they come in here like this. Okay, so there's the phase plane. And let's see what this means. Suppose that I'm sitting at rest and I give a brief stimulus, all right? So I give a brief stimulus which increases the voltage big enough to cross this blue curve. What's going to happen is, here's my picture. I'm at stable rest. If I give a little perturbation, I'll come back to rest. Little perturbation will come back to rest because this is stable. Give a bigger perturbation, and I get this periodic orbit. Now here's another cool thing. Once you're on this periodic orbit, if you time your stimulus right, suppose you time it when the voltage is down here, you can send it into here. So there's an apocryphal story. There's a story that it's probably false, about this guy that was doing experiments on phase resetting of the heart, okay? And he made a really important mistake, two mistakes. Mistake one is he didn't know nonlinear dynamics. And mistake two was he did the experiments on himself, okay? So the story goes he was doing phase resetting experiments of his heart, and the cardiac action potential can sometimes be in a situation like this, and you want that thing zipping around like this, and he gave himself a stimulus at the wrong time, went into here, fixed point, and died. Okay, so there you go. See, this is why you should learn dynamical systems, because you might die sometime if you don't. But had he known more, he would have given himself another stimulus. Stimulus would have kicked him back up, and then everything would be cool. Of course, you know, if you're doing things to yourself, you're probably, you know, drop dead. So that was the second mistake. Here's the, okay, so let's see what is going on here is, so let me start here, okay, and move in this direction, okay? Going to increase the current. What happens is this little blue cycle, you can see its amplitude is shrinking as I move this way, okay? This little blue limit cycle shrinks and hits this equilibrium point and makes it unstable. Because that's what that point you're past there. All that's left is an unstable equilibrium point and a large amplitude limit cycle. So what happens in the other direction? As we move here, this little limit cycle grows bigger and bigger and bigger. This unstable limit cycle gets bigger and bigger and bigger. Okay, you can see that. Its amplitude is growing. Okay, and then it annihilates this guy. Okay, little limits, this blue limit cycle and the green limit cycle meet and disappear, and once that happens, you're down here, and all there is a global equilibrium point. Okay, that's it. So that is basically everything I want to say about this model, this set of parameters. I'm going to do another set of parameters in just a minute. All right, this transition right around here, this transition is called class 2 excitability. Okay? And it's characterized by typically by what's called, when the Hopf bifurcation that emerges is unstable, it's called subcritical. Okay? So stable ones are called supercritical. And these are subcritical. So oftentimes, when you have a subcritical Hopf bifurcation, you very rarely see supercritical Hopf bifurcations in neural models. They're almost always subcritical. And when you see subcritical, it often leads to bistability between a large amplitude limit cycle and a and an equilibrium point. Sometimes it can lead to chaos and other things like that. Okay, do you have any questions on this? Yes?
If we will give the stimulus beyond I star and lesser than I1, then potential increases and current decreases in backward direction. How this is happening?
Wait, when I'm here? When I'm between here? Okay. How does what happen? Okay. So here we are, there's the voltage. And I give the voltage wants to be at this rest state because it's stable. If I give a little stimulus, I don't get past this blue guy. But if I give a big enough one, I do. And then it emerges into this large amplitude stable. It's a switch between oscillation and rest. Okay? So I'm not sure I understand but how does it happen? I mean, if you want a mechanism, a biological mechanism or biophysical mechanism, what's happening is when you kick past here, okay, then you're letting enough sodium in to maintain a large amplitude, excursion of the voltage, and then the potassium kicks in and brings you back down. But when you're in this region, it doesn't bring you back down to rest. There's still enough residual sodium current around to continue along, okay? So that's maybe the biophysics. Is that what you're asking? Okay. All right, so everybody good with this? This is type or class 2 excitability. Gives rise to a subcritical Hopf bifurcation and large amplitude periodic solutions that are bistable with an equilibrium point. Then out here is just a regular oscillation, okay? And what this is called the Hopf bifurcation right here. We already mentioned this, Hopf. And what is happening here is this is a stable limit cycle. This is an unstable limit cycle. And when they merge together, when you have something stable and something unstable merged together, this is called, this bifurcation is called a saddle node of limit cycles. So a stable limit cycle crashes together with an unstable limit cycle and they annihilate, okay? All right, so I'll leave this on the board for a few seconds and I'll start a new phase plane over here because I want to now change parameters a little bit, okay? Fine. I've broken all my green talk. Here we go. Be careful. All right. So, God, just erase it. Okay, now, going to change some parameters a little bit. One of the parameters I'm going to change is the shape of the end nucline. I'm going to shift it a little bit and make it sharper, okay? And I'm also going to change the M infinity a little bit, and I'm going to have a picture that looks like this. Okay? So we have this picture, all right? We have 3 equilibrium points, okay? 3 equilibrium points. So I'm going to ask some questions now, and I hope you can answer them. Okay, question 1. Is this equilibrium point stable or unstable? Stable. Why is it stable? Because the slope of this nucline is negative, right? All right, that's right. This is stable. Well, I won't put an S there. That's a stable node or something like that. What about this guy? Stable or unstable? This guy is unstable, remember, because one of the questions, one of the things I pointed out is if the slope of the V null line, remember that's the green guy, exceeds the slope of the N null line, the green guy, then the red guy exceeds the green guy, then it's a saddle point, okay? And this is, you don't know, but so I'm going to tell you, you can't tell from the picture, but we're going to assume it's unstable, okay? And remember, the determinant is positive because this slope is bigger than this slope. So it's going to be, it has two positive eigenvalues or two eigenvalues with positive real parts. Okay? So let's take a look at this for a second. I add current. This is with I equals 0, say. Okay? So then I'm going to add current, and that's going to lift this up. Okay? And we'll get to what that does in a second. But first, I want to look at what happens to the saddle point, okay? Now, do you remember yesterday I told you that for a linear system, if you had a saddle point, you had a positive eigenvalue and a negative eigenvalue. And there's an eigenvector corresponding to the positive eigenvalue, and there's an eigenvector corresponding to the negative eigenvalue, right? And things would come in along the stable eigenspace and go out along the unstable eigenspace. Remember that? Well, it turns out for nonlinear systems, there is something just like that, okay? There's a curve that comes out here that is tangent to the, it's tangent to the unstable space, okay? And it comes all the way out, and in this particular case, it does something like this. So it does that. It's kind of cool. I mean, I didn't probably draw this perfectly correctly with respect to the null lines, but you get the picture. And there's another piece of it that just goes directly over there. And what about so this is the fate of the unstable space, okay? If this was a linear system, these guys would just be straight lines and go off to infinity, right? But because it's nonlinear, they curve around and they comes back into here, okay? So now I want to draw the fate of the stable space, okay? And to do the fate of the stable space, I have to go backward in time, because if I start near that equilibrium point, because it's stable, you go into it. So I'm going to go backwards in time. Okay? What does this do? Backwards in time, this guy does this. So I want to, and backwards in time, this guy does this. Okay? So we have a picture that looks like this. I mean, this is, I've drawn it now forwards in time. I computed it backwards in time. Okay? So remember, this is an unstable spiral. And so it spirals, one piece of this spirals into here. Okay? So we have the complete picture here of this. It sort of looks like Moby Dick, a whale. All right? And this is a really cool picture, because now we have a true threshold for an action potential. Here's what I mean. Suppose I'm sitting right here at this equilibrium point, and I give a perturbation, okay? By perturbation, I mean I inject a little bit of current. What does current do? If you look at the equation, if you increase the current a little bit, it makes dV dt more positive, and it pushes V in that direction. Does everybody see that? So what happens is I give V a little kick here, and if I give it a little kick, all that happens is it comes back. because I just injected a little bit of current, not enough to go too far. And because this is stable, it'll come back. But if I give it enough current to cross this blue curve, okay, this blue curve, then I have to shoot all the way around before it can come back. So I have a threshold to generate an action potential that's a real hard threshold, okay? Any stimulus that takes me past this blue curve. This blue curve is called the stable manifold of this saddle point. And stable manifolds are really useful because they separate space. They separate things into different qualitative trajectories. So everything that starts to the left of this just makes a little blip and comes in. Anything that starts to the right makes this big action potential and comes back. Okay? Now, here's a really cool question. Suppose that I'm really good with tuning my experiments, that I can give very precise current pulses. Suppose I give a current pulse that gets really close to this. If I gave a current pulse that actually hits that blue curve, then I have to go in, right? Because it's a stable manifold. It's the guys that go in, okay? So if I gave that pulse, here's my equilibrium, I give this special pulse, I'll just sit there forever. Now, of course, biologically, that's impossible. So what happens instead is I give a pulse and I delay a long time before I finally spike, or maybe I don't spike because I wasn't quite past it. So you can get arbitrarily long delays. Here's my stimulus. You can get arbitrarily long delays from the stimulus to the timing of the action potential. Isn't that cool? And the action potential doesn't change shape because it's forced to stay outside of this yellow curve. All right. So now let's see what happens if we increase current on here. What's going to happen? Okay, you're going to lift this null line up, right? Oh. You guys are really sleepy today. If you were out drinking, I want to know where. I've been fermenting, papaya juice in my bathroom. Just kidding. I guess you could do that, though. I don't know. All right. So if I inject current, I'm going to lift this red curve up, right? So if I inject a very precise amount of current, constant current now, not a pulse. I'll have this picture. And what has happened is this equilibrium point and this equilibrium point have come together, okay? Remember, this is called a saddle, right? Remember, this is a saddle point. This is a node, right? So this is called, when these two guys come together, this is called a saddle node, all right? Just like this, unstable and stable collide, unstable and stable collide. Whenever unstable and stable collide, it's a saddle node, okay? Well, not always, but generically. In all the cases, we'll do. Well, not quite. Anyway, and then what happens if we inject a little more current, then this gets lifted up, all right? Okay? And we're left with, here I'll just draw one more picture here. Okay? We'll look at the picture. Okay? Now notice I've drawn it so that it's really close. Okay? What does that mean? Well, what's left to happen? What can happen now? This is unstable, and there's no other equilibrium points, so there's got to be a limit cycle, right? Because this, remember the Roach Motel, okay, from yesterday. So we do have a limit cycle. Kind of looks like the yellow friend here, okay? But you'll notice that it goes through this little channel here, and dVdt and dNdt are really small, because this is where dNdt is 0, this is where dVdt is 0. So along here, neither V nor N is changing very much, and you get very long periods between the limit cycle. So the action potentials can have an arbitrarily long period. Okay? So the frequency goes to 0. Okay? So we can understand that by doing some surgery. Okay? So what surgery we're going to do? I'm going to first of all, before I do any surgery, I'm going to ask what happens near here, okay? What happens in the transition from here to here. I'm not going to prove this, but it can all be proven. I'm going to just write down what's going on near there, okay? Before I do that, let me call the current here I1 again, okay? The current which this happens, okay? So this is I less than I1, and this is I greater than I1, okay? I believe Pranay is going to do this today. You're going to do the bifurcation diagram for this, okay? So near that bifurcation, the voltage has the following form. Oh, and let me call the, hold on. And let me call the voltage V1, this happens, okay? This is the equilibrium point for the saddle node, okay? Okay? Turns out that the voltage has a form like this. Now you can sort of see why it's quadratic, because if you kind of look at the null glide, it's kind of quadratic in it. And two guys are coming together. The only way to do that is to have a quadratic thing, right? You can see that near, okay, everybody see this? So near that bifurcation, locally, you have this picture. Okay? So what this says is, and B and A are positive. Now, when mathematicians want to make their life easy, okay, use the phrase code without loss of generality, all right, WLOG. And it just means that without loss of generality, I can make these both 1 to make my life easy, all right? So I'll do that, all right? Because they're going to be both positive. And why are they positive? Because we know when I gets bigger than I1, there's no equilibrium points. And when I is less than I1, there are 2. And now, I'll just translate everything by this. So I'll just look at dv dt equals v squared plus I. Okay, I'll just change my definition of I to be relative to I1 and V relative to V1. Okay, so this is a cool model because what happens to this? If I is less than 0, okay, in other words, if I is less than I1 up here, okay, if I is less than 0, then there's two equilibrium points. V equals plus or minus square root of I minus I. Yeah. Okay? You see that? Right? This equals 0 and V squared equals minus I. So take the square root. There's two equilibrium points. One to the left of V1 and one to the right of V1. Okay? But what happens if I is greater than 1? What happens if I is greater than 0 here? Okay? There's no equilibrium points. And this blows up in finite time. What do I mean by blow up? What I mean is if you start with any initial conditions and you throw this on your computer, you'll get an out of bounds error really quickly. Do you guys know how to solve first order differential equations? You have to learn that in first order separable differential equations. Let's write it down. dv over v squared plus I equals dt. Okay? And I'm going to assume I is greater than 0. And then you integrate this. Okay? And how would you do you know how to do integrals? At University of Pittsburgh, we have something called an integration bee. Okay? You guys know what spelling bees are, right? And I don't know if you knew this, but the American champion spelling bees, champions for the last like 6 years are all Indians, okay? Indians are the world champions of American spelling bees, okay? Well, at Pitt, we also have an integration bee, all right? And students come up and they have to do integrals, and they have 2 minutes to do the integral, all right? So this is going to be, I don't actually remember what the integral is. It's like tangent of something. It's like tangent square root of I or something like that, okay? In fact, I think it is. I think, here, we'll do it, all right? We want to do this integral, so we want to go from V naught, I don't want to do the integral, okay? But here's the cool thing, all right? This blows up, okay? Goes to plus infinity. So let's pretend we don't care that it goes to plus infinity, but when it reaches plus infinity, we'll call that the action potential. And then we'll take it from plus infinity and we'll throw it into minus infinity, okay? And then it'll come back, okay? Because even if you start at minus infinity, it'll still get up to close to 0 in finite time. So how long does it take that process? It takes it this long, minus infinity to infinity, and that turns out to be equal to, pi over square root of I, okay? So the period, so what's the frequency? That's the period. The frequency of the limit cycle is square root of I over pi. So the frequency gets arbitrarily low like a square root. And you'll see that today when you do this on the computer, okay? We're going to come back to this model later on, probably tomorrow, okay? And we're going to couple millions of these together, in fact, infinitely many of them, and study them. But this equation is often used as a simplified neural model, okay? So before I go on to study this, let me just do an aside and talk about some simple neural models that people study, okay? I'll just talk about 2 of them. Okay? One is called the leaky integrate and fire model. Okay? And that satisfies the following. Tau dv dt equals v leak, v rest minus v. Okay? Now this is a simple linear equation, but it has the following rule. Okay? So when V of, so if, oh, it's with the following provisos, that Vt is greater than V rest, and V reset is, and Vt is greater than V reset also. So what this does, this is basically a model for a continuously flushing toilet. All right? Toilet, I guess, is that what you guys call it here? I don't know. WC, I think, is what they call it. Yeah, toilet, yeah. All right, so let's study this guy for a second. It's a really simple model, okay? What happens is if you give enough current, if you give a current, then V is equal to, V wants to go to VR plus I, right? Steady state, right? And if this is greater than V threshold, then it won't be able to get there because as soon as it gets there. So let me draw what happens. There's V threshold. Here's V, here's T. So what's going to happen is it wants to charge up to here, but it hits here and then it gets reset and then it goes up again and you get this dumb little oscillator. Okay? This is called the leaky integrate and fire, or LIF neuron. And a nice homework problem is to figure out what the frequency of this is. Okay? So that's just a little bit of differential equations. Solve this equation with initial conditions. V of 0 equals V reset. Solve it and integrate it so it hits VT, and that will give you the period. Okay? So this is called the leaky integrate and fire neuron. This has a name. Oh, I want to make sure you don't get too confused. In the Hopf bifurcation, the amplitude goes as the square root. And in this situation, the frequency goes as the square root. So square roots are everywhere, okay? So let's do this, okay? Let's look at the quadratic integrate and fire. That's this one. Also called QIF. Okay? And the quadratic integrate and fire, typically if you're going to do this on the computer, then when V equals V spike, V goes to V reset. Okay? So now, what I just looked at, what I just told you, is let's let V spike equal plus infinity and V reset be minus infinity, and you can compute the period. If you make this finite, then the period is, computed by and you have to do this stupid integral. But I don't like doing these integrals. I don't like going off to infinity, and you can't, computers don't like infinity, right? You get not a number or something like that, right? You've probably seen that. If you have, then you're not doing a very good job of writing code. But no, okay. You got some bug in your program. All right, so what we do is I have another equation I'm going to write down. And that one is going to allow me to relate the surgery I'm about to do on this one. Okay? So here's the really cool transformation. Okay? I am starting with this equation, and I'm going to let V spike be plus infinity and V reset be minus infinity. Okay? So that's really impossible to plug into your computer. So what I'm going to do is let V of t, or just let V equal tan theta over 2. Okay? Now, when V equals plus infinity, that means theta goes to pi. And when V goes to minus infinity, it means theta goes to minus pi. So I've taken the whole line, minus infinity to infinity, and here's a cool math term, I've compactified it onto a circle. Minus pi and pi are the same damn thing, right? On a circle? So minus infinity and plus infinity are the same. So I don't even have to reset. So let's see, if we do that, and we plug that into here, what do we get? Well, dv dt is sec squared theta over 2, 1/2 d theta dt. Right? You all know the chain rule, right? Right, good. And you know how to take the derivative of tangent, good. Equals v squared, which is tan squared theta over 2 plus I. Okay? Well, so we get d theta dt equals 2 cosine squared theta over 2. Remember, sec is 1 over cosine times tangent squared theta. Well, what's tangent squared theta? That's sine squared theta over 2 over cosine squared theta over 2 plus I. Right? Oh, well, look at this. So this is equal to, I don't want to erase this. This equals so that's a really nice model, all right? Doesn't blow up or anything, okay? And it's defined on minus pi to pi, all right? And so if I is less than 0, you can solve this for a theta. And if I is greater than 0, then there's no equilibrium points in it, and it completes a full cycle. In other words, theta of t plus capital T equals theta of t plus 2 pi. Goes around once, okay? And that period t is pi over square root of period t is square root of I. No, I had it right before. Pi over square root of I. Okay, and this is called the theta model, all right? Nancy Capel and I invented the theta model in 1986. It was a lemma of another paper, and nobody remembers anything about the paper, they just know the lemma. Because what the lemma did is it showed that whenever you have this bifurcation, something like this, going to this, going to this, it's equivalent to the theta model. So let me make that more explicit by doing surgery, okay? Not surgery in the strict mathematical sense. Surgery in, like, I'm pretending to be a doctor, all right? So I'm going to rip out this pair of yellow curves, okay? And I'm going to twist it around because it's made of wire, and I'm going to get a picture that looks like this. Where'd my eraser go? Ah. You see that that's sort of the same thing as that yellow curve? There's the, and the other equilibrium's in the middle, but we don't care. We never get anywhere near there. This is also, if you look at, if you call this pi, okay, and you call this 0, this is exactly the phase space of d theta dt equals 1 minus cosine theta plus 1 plus cosine theta times I when I is less than 0. And we can figure out these two equilibrium points are. This is 1 plus I plus I minus 1 cosine theta. Right? That's just this, I've just rewritten it like that. Right? And that gives us cosine theta equals 1 plus I over 1 minus I. Right? So if I is negative, then this ratio is less than 1. And we can find the arc cosine. So this is the minus guy. So this is, I'll call this minus theta hat, and this is theta hat, and cosine theta hat equals that, okay? So all we've done is we've mapped this thing onto this very simple one-dimensional equation. And now as we increase current, what happens? These guys come together, annihilate, and leave just a circle. And it just, things just keep going around and around, right? Isn't that cool? All right, so, and it goes around at a period that is pi over square root of I. Okay? So this is called the theta model, and this reduction, this bifurcation that goes from two equilibrium points on this circle, so this goes to this, goes to that. So this is I less than 0, I equals 0, I greater than 0. Okay? And this bifurcation is called a SNCC. All right? Now, saddle node, infinite cycle. Okay? So I'll write it. Saddle node, infinite cycle. SNCC. So if you ever see the SNCC, oh, and it's also called a sniper, saddle node infinite period, okay? That's what the Czechoslovakians used to call it that when there was a Czechoslovakian country. Now it's the Czech Republic, and I don't know if they still call it that, but there was a bunch of papers by chemists, and they called it the sniper. Okay, so back to the Morris-Lecar, we can draw the bifurcation diagram for this. Oh, before I go on, suppose that I have this picture. tell me, what does the steady state IV curve look like? I'll draw 3 pictures and make it multiple choice, all right? Does it look like this? Does it look like this? Or does it look like this? Okay? What does the steady state IV curve look like? Number 1, number 2, or number 3? How many vote for number 1? How many vote for number 3? How many vote for number 2? You guys don't vote, you're going to get Trump. Okay, it is number 2. Okay, so that's what the steady state looks like. And so we know that if we flip that around, we'll get what the steady state bifurcation V as a function of I looks like. So that's easy. So we have for the we have this picture. All right, so we know this is a fact, right? This guy's always stable because that's that is this guy. We know he's always stable. We know that guy's always unstable. And we don't know about this middle guy right here, okay? But we know at least near this bifurcation, it was unstable. So that's why I've drawn it with a dashed line. And up here is our old friend, turns out to be our old friend, the Hopf bifurcation, okay? But we don't care about that because that's for really high currents, okay? By then we've killed the axon. Oh, did you see I have an octopus on today in honor of the squid? Okay, these are the same guys, basically. Except squid is easier to eat than octopus. Octopus is tough. You have to cook it exactly right. All right, so what happens now to this limit cycle? Well, I'm going to draw the limit cycle, and I'm going with protocol, and I'm going to draw the maximum and minimum values of the voltage for the limit cycle. Okay, so up here we have the maximum, down here we have the minimum, and then as predicted by general principles with neurons, the subcritical hop up here, back here, but we don't care about that. We're only interested in up here. So what happens here is this limit cycle dies exactly here. So there's a limit cycle. There's a limit cycle just at this point, and then over here is the shadow of that limit cycle. Okay, so there's those 2 fixed points. Then it goes to 1, and then you're left with that cycle. Okay? So now there's no bistability. We go immediately from steady state to a limit cycle. Steady state vanishes into an infinite period limit cycle, and then you're left with that. Okay? Question? You'll have to speak. Oh, yeah, that's a good idea. I like that. Microphone.
What do you mean by the shadow of the limit cycle there?
There's no limit cycle anymore, but it's, there's no limit cycle anymore, but that circle remains. Because remember, that's this circle, this yellow circle. Okay?
It's a bistability region.
Huh?
It remains a bistable region there. Like
I still can't hear it. Speaking loudly into it.
it still remains a bistable region there at that region, right? The Hopf bifurcation, right there.
I'm sorry, I still can't. Pranay?
So it still remains a bistable region there at that moment of time. I'm not the limit cycle there.
Oh, that's not a limit cycle because it ends up, it gets stuck on the fixed point, equilibrium point. It never gets past the equilibrium point. Yeah. It wants to be a limit cycle, but it's a wannabe limit cycle, but it keeps getting stuck. Okay?
You said that there is no bistability now.
Yes.
In the previous,
I mean, there's stability on this end, but not here. There's all that's left is a stable, there's either a stable equilibrium or a stable limit cycle, but never two things simultaneously. See, you immediately disappears. Is that clear? All right. So this is the SNCC, all right? Now, I'm going to keep this bifurcation diagram up, and I'm going to change a parameter in the Morse-Lacard equations. I'm going to make tau n a little bit smaller, all right? Okay? And I'm going to show you that, notice if I change tau n, it doesn't change the IV curve because it doesn't change the equilibrium points, right? You see that? It can't change the equilibrium points because n is still at infinity. It doesn't matter what tau n is, okay? All right, let me draw the bifurcation diagram when I've made tau n just a little bit smaller, okay? Okay, we don't care what happens out there. Okay? And now, where's my limit? My limit that goes green. Okay? Now you'll notice what happened here is this limit cycle died exactly at this point. Okay? See that? Died at that point. That's why there's no bistability. Okay? And that happens if tau n is big enough. Okay? Always will die that way. But instead, what happens if tau n is not so big is it gets past that and then it dies here. Okay? And I'm going to show you what this means in just a second. So we have a periodic orbit here. And now, I should have probably used a different color than green. Here. I'll stick with okay. This, and I'm going to draw it on the phase plane for you. Here, the limit cycle died on the saddle node. Okay? Here, it died on the saddle. Remember, that's a saddle point. So, if the limit cycle is zipping around like this, in that direction, it means it had to look something like that, right? So this had to be the unstable subspace of the saddle, remember the unstable manifold, coming into the stable one. So the unstable and the stable guys join together and form the closed thing, okay? This is called a homoclinic bifurcation. All right, I'll ask you this. Is there bistability? I'll make it multiple choice. How many people say yes? All right. How many people say no? Okay. Oh, yeses. There's more yeses. Okay, look at this, all right? If we look at the region between here and here, the homoclinic bifurcation, you can see that there's a stable limit cycle and a stable equilibrium point. Okay? So the answer is yes, there is bistability in the homoclinic. So now I'm going to draw it on the face plane. It's going to take me, it might take me 1 or 2 tries because it's always tricky to draw it in the face plane. I have a question before I continue. Is there a culture of belief in aliens in India, like from outer space? Because in the US, there's a lot of it. You know, we believe in all kinds of cool conspiracies. We have an Area 51. Aliens always have a particular look to them. And you're going to see that this phase plane is going to look exactly like the aliens people in the United States believe in. Okay? All right, so I'm going to draw the phase plane right around here, okay? Right from here back, okay? Okay? So there's always going to be 3 equilibria. 1, 2, 3, okay? That's why I'm keeping away from this region, okay? It's 3 equilibria. Now let's see. I have to think about this. All right. Yeah. Gesundheit. I have a lot of trouble with the chalk here. It's not your fault, and not the chalk's fault. I'm really bad with chalk in general. Yeah. All right. You see my little bird there, right? Now I want you to carefully watch. This is the saddle point. This is the stable manifold of the saddle point. This is a stable equilibrium. This is an unstable node, or spiral. So if I start here and I give a perturbation that goes past there, I have to make a big loop before I come back. So I have the same sort of thing as I had before. I have action potentials. Okay? So this is at this point right here. This is I1. Okay? Past this, but still where there's 3 equilibria. Okay? All right? And now I'm going to draw a picture at I3. Okay? I3 will be right here. Okay? I1, I3. Still not at the saddle node. I'm skipping the homoclinic because we're going to glue that. We're going to figure that picture out by looking how you go from one to the other. Okay? So I'm going to draw my same 3 equilibria over here. 1, 2, 3, okay? And that's this nice stable limit cycle that's in here, okay? Remember, we're in this region, we have a stable limit cycle. Does anybody see? Remember, all right, let me blow this region up a little bit so it's easier to see. Getting crowded there. All right, so let me draw this picture again. Okay, we have a stable limit cycle. I don't want to draw that at high. Can't reach. Oh, it's too hard. All right. So our limit cycle came in. Our limit cycle came in, say, right here. Now I want it to come in farther. Limit cycle came in here. Here's our homoclinic. Okay? There's that homoclinic. So this is I1. This is I3. See, there's this nice periodic orbit here. And a stable fixed point. And we're away from the saddle point. Okay? Saddle point, stable equilibrium, periodic orbit. Let's look at the stable manifold. He has to do this. Okay? So he does this. So we have bistability between a limit cycle and an equilibrium point. So before we go on to how we get from here to here, I want to look at this. This is really cool. Why is it cool? If we start at the equilibrium point and we give a big current, okay? A big current pulse, something like that, okay? What does that do? It pushes the voltage all the way over here and we just come back down. If we give an intermediate one, then we get caught into the limit cycle. And if we give a small one, we go back. So this thing has 3 distinctive behaviors depending on the size of the pulse. It's bistable. There's the limit cycle and the fixed point. And when we're on the limit cycle, we can give a perturbation in this direction or this direction to bring us back down. Okay? So how do we get from here to here? Well, I want you to look. Here, the yellow is outside the blue. Right? Yellow, blue. Blue, yellow. Let me erase that white line so it doesn't too confusing. So yellow, blue, blue, yellow, like IKEA or Sweden. All right. You don't have IKEA, I guess. Huh? They're a Swedish furniture company. You have to build it yourself, and it's all written in Swedish, so you can never figure out what's going on. All right? So here we had yellow outside blue, blue outside yellow. as we move from one to the other, there must be a place where blue and yellow hit, right? Because blue is here, yellow's here. Afterwards, they exchange. There must be a point where they hit. That's the homoclinic. So let's draw that. There's our yellow out. And there's our blue going out. There's going to be no talk. And there's an equilibrium point up there. And, okay. So you can think of this. This has got a finite period. Okay. It's a limit cycle that has a finite period. You can think of this as a limit cycle that has an infinite period, because it takes infinitely long to get out of here and infinitely long to come in. So there's an exercise in my book where you can compute the period of this bifurcation. And it basically goes, remember in the saddle node, the period was pi over square root of I as I goes to 0. Okay? In the homoclinic, it is roughly, this is I2. The period is roughly, I think, natural log of there. Okay? So if I is getting closer and closer to I2, this is going to 0, this is going to minus infinity, but so minus infinity, it goes to infinity logarithmically, okay? So the frequency is also going to 0, but not like a square root, it's going like 1 over log, okay? Okay, so 6 minutes left. Here's a question, Prane. It doesn't make sense at this point for me to go to the next topic with only 6 minutes left.
We can stop.
So I think, oh wait, no, you know what? I'll use the last 6 minutes to set up the next thing that I want to talk about. All right. So what we've done here, oh, no, you know what? Should I do any bursting or not? What?
No, I won't do any bursting in the tutorial.
There wasn't any bursting? Or was there? Did I mention bursting? I guess I don't have it in my... So, I was wondering...
You were going to do a little bit.
Huh?
You were going to do a little bit. Yes.
I was going to do bursting? Oh, okay. Well, then we'll do a little bursting now. Okay? Bursting's fun. Okay? Okay. I just do a little bit. Bursting, what is bursting? Okay? Bursting is a kind of firing that neurons do where instead of doing a spike, they do groups of spikes, bursts of spikes. They go. So bursts will look like okay? So that's a burst, all right? And there's there's two really easy mechanisms to get. There's back in the 1980s, John Rinzel and Artie Sherman started to classify bursts, okay? And the way you can think of a burst is a transition of a parameter as it sweeps through a bifurcation diagram, okay? So let's take this case of the homoclinic, okay? Right here. Suppose that we had some way of feeding back I onto, suppose instead of making I constant, we make I a variable, okay, that is somehow dependent on the voltage, okay? So we're going to have an addition, we're going to go from 2 dimensions to 3 dimensions. Now, typically you don't use I, you have another current in there. But in the interest of simplicity, I'm going to let I be a variable, okay? So I'm going to take the differential equation, oh, that is a nasty looking eraser. And now I'm going to let, just because in the interest of time, di dt equals epsilon times h of vi. And I'll define this in a second, okay? Now, for those of you who aren't mathematicians, in math, 99% of the time when you see something that is epsilon, it means epsilon is small, okay? So epsilon's going to be small. In other words, I is going to change very slowly, okay? So this isn't a good biophysical model for bursting, but it's a good conceptual model. So let's go to our friend here, the homoclinic bifurcation. And I'm going to draw it over here again. And there's a homoclinic, okay? And let's suppose that we do the following, and remember what is on this axis? Vi. Now I'm going to define, okay. So let's suppose that when we're at rest, okay, when we're down here, okay, let's suppose that down here, di dt, in fact, let me do it this way. I'm going to make it real easy. I think this will work. I think this will work, okay? V tilde is just a parameter, okay? And if V is less than V tilde, the IDT will get big, right? Will start to grow. Do you see that? Okay? So I'm going to make V tilde. Oh, okay. All right. So there. Does that mean it's time to stop? All right, because the little alarm went off. I will pick up. All right? And we'll do bursting. I don't know whether I was supposed to do I couldn't remember whether I was doing bursting or not. Okay, so bursting is really fun, okay? All right, so we'll stop here.